So this section is talking about changes and properties. And changes can be physical or chemical. In a physical change, we're changing the appearance of a substance or its state, but we're not changing what it is. Okay? So here we have an example of a pot of boiling water. So this is liquid water, and it's undergoing a change. It's going from liquid to a gas. But if we could look at the individual particles, they're still little water molecules, right? So it's like students in lab leaving through the door and separating, right? Your person, your body doesn't change. All that changes is that you're not close to the other people anymore. Okay, so that's what a physical change is. The stuff doesn't change. The substance doesn't change. Yeah. It looks like it changed, right? You know, ice melts, it looks different, but it's still the same stuff, same particles. In a chemical change, those individual particles do change. And so this would be something like an iron nail that's rusting. So originally, the nice shiny nail was a crystalline substance here with iron atoms only, all lined up nicely. What happens when it rusts is it combines with oxygen and forms something new, iron oxide, which has a different appearance and different chemical and physical properties. And so we see that the nail went from all shiny and smooth to being this, rusty color and bumpy and starts to flake off, right? What happened is that these particles rearranged and combined with other particles, and so now zooming in on the atoms or molecules, we can see that they're different. That's a chemical change. Okay? We've got a new substance being formed. Here we've got dry ice, solid carbon dioxide. So it looks like this frosty stuff. Dry ice is kind of neat. I was going to say it's cool, but it's cool. It's cold. It is cool, but dry ice is cool because it doesn't melt. That's why they call it dry ice. So you can use it to keep your stuff cold, but it doesn't ever melt and make a mess or get your sandwiches all soggy. What it does is it sublimes. It goes straight from a solid into the gas. But looking at the particles here, the particles are the same, and so that's a physical change. All that's changed is how the particles are relating to each other. What they actually are didn't change at all. Here we have sugar dissolving in water. So here we have the sugar molecules, and they're in these sugar crystals, and we're going to put this into some water and stir it up. And now what we see is that the dissolved sugar is swimming around in the water, but these individual particles, these molecules, are the same as they were before. Now they're just mixed in with the water, but the particles are the same. So again, that's a physical change. Okay? Here we have propane burning. So here are propane molecules, and they're coming out of this tank, and there's this little camping stove here, and you ignite it. And what happens is the propane combines with oxygen and forms two new substances, carbon dioxide and water. And so we see that these particles are different than those particles. The particles changed. So chemical change. Does that make sense? We can also identify properties. So a physical property you can observe or demonstrate without changing the composition. So gasoline has a particular smell. When you smell the gasoline, you don't change the gasoline into something else. When you look at this piece of paper and say, that piece of paper is yellow, did I change the particles of the paper? No. What if I rip the paper in half? That was pretty good. Are the particles of the paper different now? No, it's just these guys got separated from those guys. So that's a physical change. The physical property has changed now. This, if you measure the length, you can measure the length of this. The length has changed, but the substance hasn't changed. So the color, the taste, the appearance, melting point, boiling point, density, you can observe all of those things without changing what the substance is. A chemical property is related to a chemical change. If you observe the chemical property, it's essentially a chemical reaction. Observing the property, you have destroyed the original thing and created something new. So gasoline burning, similar to the example in the picture with the propane burning, the propane molecules are destroyed, and we've got new particles that are formed because a chemical change happened. Corrosiveness, where acid erodes concrete or a metal, that's a chemical property, and when we observe it, the chemicals change. There's a chemical reaction. Any questions about that? So this is along the lines of questions that could show up on an exam. Determine whether each change is physical or chemical, and what kind of property is demonstrated in each case. So a copper wire is hammered flat. This can be a physical change, because are the copper atoms getting smashed? No, they're moving because it's being flattened, right? So that's going to be a physical change. And the property there is copper wire will flatten out when you hammer it, right? So is that a physical property or a chemical property? It's a physical property. So, physical property. A nickel, like the coin, dissolves in acid to form a blue-green solution. That's a chemical change. One of the clues here is that there was a color change. Color change is often associated with a chemical reaction. So nickel dissolving in acid, is that a chemical property or a physical property? Chemical. Dry ice sublimes without melting. That's going to be a physical change. Really should change that one because we just had that as an example. And so then that would be a physical property. A match ignites when struck on a flint. That's going to be a chemical change. Because you can't light that match again, can you? It doesn't work anymore. And so that's also a chemical property. Okay? When I ask test questions, I try to make questions that should be obvious. The nickel dissolving in acid, that one's a little sketchy. Diagram on the left, that's this one, represents liquid water molecules in a pan. Which of the diagrams, A, B, or C, best represents the water molecules after they have been vaporized by boiling? So if I take this water and I boil it, does that change what the particles are? It just changes how they are relative to each other. Are they close or are they far apart? So which of these would represent the same particles, just separated?
Or B? I feel like if it's vapor though, wouldn't it be faster, so wouldn't it be C because the atoms are going apart faster?
I totally see where you're going with that. I totally do. But if we look at these individual particles, those are not the same as these individual particles, right? So these are molecules which are composed of atoms. And so over here, we've separated the molecules into individual atoms. But for this to be a physical change, boiling, it has to be the same molecules. Okay, so which one is the answer? It's A. Oops. Okay. So sometimes these picture questions end up actually being trickier than the word problems because they really get at, do I really understand what that means? Any questions?
So when you boil something, it's still going to be a physical property?
That's a physical property. The physical property would be like water boils at 100 degrees Celsius. You identify the boiling point. The change that it undergoes is going from a liquid into a gas, So it's changing its physical state, that's just a physical change.
Okay.
Yeah, and then if you take that steam that comes up and you collect it and you cool it down, it's liquid water again.
So that's physical still. But if you boil the water and the whole room was filled with like CO2 and they combined it, would that be chemical?
Well, if the boiled water underwent a chemical reaction with the CO2, then yes. But that would be different than the water boiling itself, right? Yeah, good questions. Anybody else? Oh, thank goodness.